Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for today, we are going to present to you a topic in optoelectronic subject, which is the Fabry Perot Homojunction laser diode, or we just call it as FP laser diode. So before we start, I'm going to introduce to you our group members. First, we have Abdullah Solihin bin Muhamad Fauzi, me myself, which is Ahmad Syahmi bin Muhamad Zain. Then we have Muhammad Afifi bin Muhammad Noor, and lastly Noor Hannan Ajwa Binti Muhammad Fauzan. So we will go to the first topic, which is what is FP Perry laser.
What is Fabry Homojunction laser or FB homojunction FP aja. Okay, before we go further to explain what is Fabry homojunction laser diode, first we must know what is laser. Laser is light amplification by stimulated emission of radiation. So here I stated the advantage and also the disadvantages of laser. For the advantages, first we have the extreme narrow spectral width or line width. Second is source of coherent light. Third is laser can be modulated very fine, and the last one is inexpensive for laser diode. For the disadvantages, we have 3 points, which is the first one is laser need temperature and output control, and this is very highly cost. For the second one, for optical communication system. For optical communication system, a cooler Peltier effect is needed. Okay, the Peltier effect here is the absorption of heat in junction of two metals. That is the definition of Peltier effect. The last one is the analog modulation is difficult due to the non-linearity of the output power. Okay, next we can see the homojunction. Okay, here is what is the homojunction. For the definition, a homojunction is a semiconductor interface that occurs between layer of similar semiconductor material. So the highlight here is the layer of similar semiconductor material. So in the picture here we can see for the P-type and the N-type here, the semiconductor material used is the same, which is the gallium arsenide, and also the N-type, also the gallium arsenide. Okay, the homojunction occur at the interface between N and the P-type, and this region we call as the PN junction. Okay, besides we know that the material used is similar, the equal gap. So here the P-type and the N-type has the equal band gap. So this is also makes the homojunction occur. This is the definition of the homojunction. Okay, next is the classification. Okay, for the classification of semiconductor laser, we have two types, which is the first one, the homojunction diode laser, and the second one is the heterojunction diode laser. For the heterojunction diode laser, also divided by two, which is the double heterojunction diode laser and also the single heterojunction diode laser.
What is Fabry Perot? Fabry Perot is a combination of two French scientists, which is Charles Fabry and Alfred Perot. So this laser is conceived of two facing, two flat reflecting, two flat mirror, which are facing each other. So the laser will reflect and will go to the output, if you can see in the as in a figure. So the losses of some frequency are composite because this cavity has a game mechanism. So we will finding there are some frequency are losses and some frequency are gain. The next standing wave with longitudinal wave can only propagate. So, for the characteristic, the type of laser, it is a solid state semiconductor, and for the active medium, a PN junction diode from single crystal of gallium arsenide. This laser also can only produce about 1 milliwatt for the output power, and for the nature of output, this laser is a continuous wave of or pulsed output. So we move to the equation. we consider these Fabry period are relatively short cavities. So from the equation we can calculate the length of the cavity, which are lambda s over 2n. S, which is the arbitrary integer, and for the n there is a for the refractive index of active medium.
Next, we will see how it works. Before we start, we need to know the structure of the FP laser, which is it contains two parallel mirror and also active region. The two mirrors and the active medium between them will form a laser. This is shown in this figure. We need mirrors to provide positive feedback. That is the return of stimulated photons to an active medium to stimulate more photons. The two mirrors themselves form a resonator with length L. Let a random wave travel from the left-hand mirror to the right-hand mirror, as the second picture here shows. At the right-hand mirror, this wave is reflected. Hence, the wave experiences a 180-degree phase shift. As you can see, the wave should have a break in this phase, which is impossible here. In the other hand, this resonator does not support this wave. Let's move to another wave, as shown in this figure. This wave travels inside a resonator. At the right-hand mirror, the wave experiences a 100-degree phase shift and continues to propagate. At the left-hand mirror, the wave again has the same phase shift and continues to travel. Thus, the second wave uses a stable pattern called a standing wave. The only difference between the two waves is their wavelength. Thus, a resonator can support only a wave within a certain wavelength, the wave that forms a standing wave pattern. This resonator supports many wavelengths that can form a standing wave. Wavelengths selected by a resonator are called as longitudinal modes. How many longitudinal modes can a laser diode radiate? A resonator can support an infinite number of waves as long as they form a standing wave. However, the active medium provides gain within only a small range of wavelength. Since a laser radiation is the result of the interaction of a resonator and an active medium, only several resonant wavelengths that fall within the gain curve might be radiated. This is shown in this figure. Of course, light generation starts only when gain exceeds loss. Thus, eventually only those resonant wavelengths that are within the gain over loss curve will actually be radiated. Compare these two figures. Only these three will be actual laser output. The other two modes are not generated since their loss is bigger than their gain.
For the applications, there are two types of Fabry Perot. The first one, underwater laser. The second one is laser range finder. Moving on to the underwater laser, this laser can be used as underwater transmission. It also uses distance measurement. The latest technology for submarine is sonar, but it can be full of noise and not practical. The laser can replace sonar to avoid obstacle and mapping underwater. Next is laser range finder. Laser range finder works by emitting laser beams at the push of a button. The beams bounce off distant object, and the range finder's high-speed clock measures the total time it took when the beam left the unit until it returned. Using that time measurement, the range finder calculates the distance and displays it to the user. That's all from us. Thank you.